Okay, today we're talking about mass stoichiometry, and I need to be honest with you, this is one of those topics that has struck fear into the hearts of chemistry students for a very long time. However, I want to assure you that there's a pattern that you need to follow, and as long as you follow the pattern and you're paying attention to the things that really matter, and I'm going to say the units, then it's actually not that hard. It actually starts to fall into place, and it should even make some sense. We're going to start, however, with making a sandwich. We're not actually going to make a sandwich, although I would really like this sandwich. But if I made this particular sandwich, that becomes the recipe for the sandwich. I need 2 slices of bread, 1.5 tomatoes, and I know that's a really weird amount of tomatoes, and I'm not sure if it's 1.5 slices or actually 1.5 tomatoes, and it doesn't really matter. 4 slices of bacon, and that's going to make a proper sandwich. I prefer the more tomato. But the point of what I'm talking about here is if I needed to make more, if I wanted to scale up that recipe and make 5 sandwiches, well then I would need 10 slices of bread, whatever 5 times 1.5 tomatoes is, and 20 slices of bacon. I'm going to pause there for a second and think about that much bacon. If I want to make 500 sandwiches rather, or 5,000 sandwiches, the recipe would stay exactly the same, and all I would do is scale it up. I would take exactly the same proportions and apply it to new amounts. And at the end of the day, stoichiometry is basically that, except we don't eat it. Stoichiometry is, in our case right now with mass stoichiometry, it is the mass relationship. So instead of counting out slices of bread or numbers of tomatoes, I would count out masses of tomatoes or mass of bacon. Still not eat it. Now, if I take a reaction, and I think about it in the terms that it is given in the balancing numbers, those balancing numbers are helpful, but they're never going to be the actual amounts we're using. They just represent the recipe. So if I take, for example, this reaction here, the thing I want to, or the way I want to read that reaction or understand that reaction is in terms of molecules. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make, in this case, 2 molecules of ammonia, NH3. So if I were to use that as my recipe and say, well, fine, how many molecules of hydrogen do I need to make 72 molecules of ammonia? I think you would know what to do. You would say, that's the recipe, those are the proportions, let's scale it up and use a ratio, and that's exactly right. I want to point out a couple of things with this ratio though. Number one, it's really important that we get the numbers right? So I put the thing I'm looking for on top. I put the recipe on one side. So the 3 hydrogens over the 2 ammonias, that's my recipe. That's always going to be in a particular spot. The thing I'm looking for goes on top. Now I say that because oftentimes when we're solving ratios, the ratio is kind of given to us, or it's a little bit more obvious, or there's fewer numbers that I have to pick from. Like I didn't do anything with the nitrogen, for example. Second thing I want to point out is I have the labels in there, and I put the labels in there, and I think they're really important in order for us to keep track of what it is that we're dealing with. However, if I were to solve that ratio, and we don't need to walk through the math because we all know how to do that, I would get 108 molecules of hydrogen following the same recipe. However, we do reactions according to numbers of moles, so I need to rethink that reaction, but kind of keep it similar. So now it's 1 mole of nitrogen reacting with 3 moles of hydrogen to make 2 moles of ammonia. And in that sense, the moles are going to keep the numbers exactly the same. But now I can have fractions of moles. So where I couldn't have 4.8 molecules of NH3 ammonia, I can have 4.8 moles. But if I ask pretty much exactly the same question in terms of its content, then I'm going to have exactly the same ratio. I'm going to have my recipe, but now that recipe doesn't represent molecules, it represents moles. So 3 moles of hydrogen makes 2 moles of ammonia. So then how many hydrogen would make 4.8? And I would do the math in exactly the same way. And again, we don't need to work through the math. We know how to solve ratios. But notice it starts to look a little bit more complicated because now I'm dealing with moles. I've got the units in there. And by the way, the units are really important, and we're going to need to track those units, much more important than the numbers, I would argue. Okay. If we try a similar thing, except now looking at 2 different things, we're going to set up a ratio in a fairly similar way. How many moles of nitrogen are needed to react with 7.58 moles of hydrogen? Well, in that sense, my recipe is slightly different because while the 2 moles of ammonia are still part of the reaction, they're not the parts that I'm looking at. So now I'm looking at two different things, but the approach is exactly the same way. I set up my ratio using the recipe on one side. The thing I'm looking for goes on top. Can it go somewhere else? Of course it can go somewhere else, but it's important to always do a similar thing, to set things up in a consistent way. And later on, I'm going to show you something where setting it up this way works a whole lot better. And some of the other ways that you set it up is just going to confuse you because you're going to have to like unlearn something to relearn it a different way. Okay, but I'm going to do the math exactly the same way. It's still a ratio. I'm still just solving for that ratio. By the way, if you haven't pushed the buttons and done these on your own, if you've just been writing the answers down, you really need to go back and push the buttons because it's going to help you understand when you see where those numbers come from. So for example, this one, you can now try this one. I'm not going to work it through. I'm not going to set up the ratio for you. I'll show you what you should get as a final answer. But make sure you set up the ratio so that the recipe that you're dealing with, like what am I working with, what am I trying to find? Here I've got 5.6 moles of water, and I'm trying to figure out moles of oxygen. The balanced chemical reaction provides me the recipe, and I hope that language makes sense because I'm going to keep using it, the recipe for this reaction. And when you do that, and hopefully you paused for this, you get 7.6. And again, if you have not paused the video to set up the ratio and find out if that's the answer you get, please do so. It will be very, very helpful. Okay, the problem with what we've done so far is while it is really, really important and it's going to be a piece of what we do, we haven't talked about masses. So mass stoichiometry, we got to bring masses into this. And keep in mind, we actually measure masses. We don't work with moles directly. We measure masses or volumes of solutions or pressures and temperatures and volumes of gases. We have these other things that we work with in order to figure out numbers of moles. Okay, so a typical question is going to look like this. We're going to actually work through the first one, maybe not the second one, but taking a look at those questions, they should be at least logical or sensible in terms of what we're trying to accomplish. So let's take that first one. What mass of hydrogen is required to react with 31.6 grams of nitrogen? And the reality is it's a fairly similar kind of question as what we had before, except now it's asking for masses. Well, what I'm going to do is I'm going to follow this plan. I'm going to take the mass that I know, that was the mass of thing, and I'm going to turn that into numbers of moles. So how many moles of nitrogen are in 31.6 grams of nitrogen? I was given a mass, I need moles. Well, how do I find numbers of moles? Well, I take the mass divided by the molar mass. I like to carry units all the way through. You don't necessarily have to, but you definitely need to have moles of nitrogen on the end of that. And again, if you haven't pushed the buttons on your own, please do so. But I really want to find about numbers of moles of the other thing, that ratio we were doing a few moments ago. So I'm going to now ask the question, how many moles of hydrogen would I need to react with that number that I figured out the last time, moles of nitrogen? Set up the ratio in the same way. The recipe from the balanced chemical reaction, but then also the scaled version that I'm dealing with in this particular case. Solving for x, and notice I set the ratio up exactly the same way, and I always will. 3.386 moles of hydrogen. That is a really large font. Why? Anyway, now, you don't need to write this part down. You don't need to really think on this too much, but this is the question of, if I've done those two steps, how many moles of hydrogen for that mass of nitrogen? See how we're kind of getting there? Okay, but the last step is to turn it back into mass because that was really the question, what mass? So take that moles of unknown, which we now know, of course, and turn that into a mass. So my known and unknown were just the identities of the chemicals that I'm using. Okay, so in other words, what mass is 3.386 moles of hydrogen. Well, the mass of that is the number of moles times the molar mass. And I multiply those two together and I get 6.77 grams. In other words, I started with a mass of nitrogen, and I've gone through 3 steps and I figured out a mass of hydrogen required. And that middle step was the thing we were doing before with the ratio. Now I really want to emphasize that you cannot do this in any shorter than these 3 steps. These 3 steps must be done every single time. Later on, if you're doing stoichiometry of solutions, there will be 3 steps, slightly different. Later on, if you're doing stoichiometry with gases, there will be 3 steps. Slightly different, but the same basic 3 steps. I have to convert mass into moles of the thing that I'm given in the question, turn that into numbers of moles of the thing I'm looking for, turn that into the mass of the thing that I'm looking for. Every single time. There's no shortcuts. Okay, let's try one for this. So a different reaction, because why not? What mass of carbon dioxide is produced if 53.6 grams of water were also produced? And I want to just pause here for a second and say, with stoichiometry, it doesn't matter how big the reaction is, doesn't matter how many reactants, how many products there are, doesn't matter how many balancing numbers there are, it doesn't matter if it's 2 reactants, 2 products, 1 of each. We're always going to do exactly the same thing. It's always one thing that we know and one thing that we're looking for. All the other stuff we just assume takes care of itself. Anyway, here's my plan. I'm going to convert from the mass that I know into the mass that mass that I know into moles of that thing. And I'm going to use this formula to do it. Then I'm going to turn the moles that I just calculated, the moles that are known, to turn that into the moles of the unknown using that ratio. Then I'm going to turn that moles of the thing that I'm looking for into mass using number of moles times molar mass. Too easy. Okay, first step, mass of known to moles of known is the 53.6 grams of water divided by the molar mass of water to turn that into number of moles of water. Second step is moles of known into moles of unknown. That's my ratio step. That's using the recipe from the balanced chemical reaction. Well, the recipe is on one side. How many carbon dioxides do I get with that many waters in the balanced chemical reaction, and what does that mean for my scaled version of the recipe, the version of that reaction that I'm using right now? Solve the ratio and I get 2.235 moles of carbon dioxide. That is not my final answer because I need to know the mass of that. So now the question is, what mass do I have from that number of moles of unknown? Well, I'm going to do number of moles from the previous step times the molar mass of carbon dioxide, and that will give me my final answer. Okay, I'm going to leave this one more or less with you, and then we'll come back in a minute and tell you the answer, so please pause and come back. Okay, step 1, if you paused, if you didn't, that's the answer to step 1. Pause for step 2. Step 2 gives you that. Pause and do step number 3, or go back and figure out where you went wrong on this one, follow the steps as we had it, and then step 3. Too easy. Okay, this one I'm really going to leave with you. Another reaction, another recipe, another mass, but it still is going to be the same thing. I'm given a mass, I'm asked to find a mass, I must do 3 steps every single time. Okay. Big picture stoichiometry, and what I was talking before about the solutions and the gases, there are things that I can measure. There are things that I work with, but reactions always function according to numbers of moles. So it'll always be that thing that I measure. Volume of a solution, temperature and pressure and volume of a gas, mass of a solid. Turn that into numbers of moles of the thing that I'm given. Turn that into number of moles of the thing that I'm looking for. Turn that into some other measurable mass, volume, temperature, pressure, and so on, and volume of a gas. Okay? That's all stoichiometry is. However, it's always those 3 steps. I had 4 fingers there. Those 3 steps every single time. That's it for stoichiometry, for mass stoichiometry. It's going to feel a little bit overwhelming at first until you learn the pattern, until you kind of get your own system going of understanding. I'll give you some tips in class when we talk a little bit about it. However, it does come down to these 3 steps, getting them up here as quickly and as efficiently as we can. Talk to you another time.